Hi guys, and welcome back to the Tech Crux. In this video, we will discuss about the multiplication rule and conditional probability. First, let's start with the multiplication rule. Consider independent events where the occurrence of one of the events does not change the probability of occurrence of the other events. In the previous video, we took example of placing order for either a burger or a pastry. Now, if we wish to have both the items, then what will be the probability of that happening? So, here we need to know probability A and B, which we will write as probability of A intersection B. And for that, we will multiply the individual probabilities of both the events, since both are independent events. Here the probability of A intersection B is known as joint probability. And these individual probabilities are known as marginal probabilities. In case of non-independent events, we'll write it as probability of A multiplied by probability of B given A, or this will be equal to probability of B multiplied by probability of A given B. This is known as conditional probability of B given A, or the conditional probability of A given B. It tells about the probability of occurrence of an event given another event has already occurred. In our example, probability of A given B is the probability of ordering a burger given the pastry has been already ordered. Now let's talk about three events. In that case, the probability of A intersection B intersection C will become probability of A multiplied by probability of B given A multiplied by probability of C given A intersection B. Similarly, for any n number of events, we can write it like this. Or in simplified form, it becomes like this. Here we are using the product notation. From I is equal to 1 to n. Now let us discuss the concept of conditional probability in detail. It is the probability of occurrence of an event given another event has already occurred. Before moving ahead, consider that here A and B are collectively exhaustive, non-exclusive, and non-independent events. So, as they are collectively exhaustive, that means there are only two items available for placing the order. Therefore, the probability of A plus probability of B will comprise our sample space whose probability will be 1. Further, since they are non-exclusive, so ordering one of them does not stop us from ordering the other item, so we can say that the probability of A intersection B is not equal to 0. And for these events to be non-independent events, ordering the one conditions on ordering the other, and the probability of A given B is not equal to probability of A, or we can say that the probability of B given A is not equal to probability of B. Now, considering that the burger has been already ordered, in that case, what will be the probability of ordering the pastry? Recall from the multiplication rule of non-independent events, the probability of ordering both when burger has been already ordered is probability of A intersection B, that is probability of B given A multiplied by probability of A. We can also write it as probability of B given A, which equals the probability of A intersection B by probability of A. For example, consider that probability of ordering the burger or happening of event A is 0.4 and probability of ordering both burger and pastry is 0.2. In that case, if we find the probability of ordering the pastry, when burger has been already ordered, it will become 0.2 upon 0.4, which equals 0.5. Similarly, we can also calculate it for any event when n-1 events have already occurred. Consider having events A1, A2, to AN. Then, probability of AN given the other events have already occurred, will be written as probability of events A1 intersection A2 to AN upon the probability of A1 intersection A2 and so on, to AN-1. And that's how we can calculate it for n events. Alright, now let's take an example problem which says that, in a survey it was found that 60% people speak English, 40% speak German and 20% speak both. Now, if a person is chosen at random and if he already speaks English, then what will be the probability that he also speaks German? And the following are our options available: 5 by 12, 3 by 16, 1 by 8, and 1 by 3. So, here we are asked to find probability of person speaking German given he already speaks English. Using the conditional probability, we can easily estimate probability of person speaking German as the ratio of probability of English intersection German to probability of person speaking English. So, this will be 0.2 upon 0.6, that will be 1 by 3, or we can say that there is 33.33% probability that the person speaking English also speaks German. Therefore, option D is the correct answer here. Now let's have a look at one more problem. This one here says that the following information has been gathered while analyzing the causes of power failure in a city. 20% due to transformer damage, 60% due to line damage, and 4% due to both the issues. So here, we have for a power failure, the probability that it is due to transformer damage is 0.2, probability that it is due to the line damage is 0.6, and probability that it is due to both transformer and line damage is 0.04. Now further it asks us to estimate the probability of a given power failure involving line damage, given there is a transformer damage. We have all the information available with us which we require, so we can calculate probability of line damage given there is a transformer damage, which will be ratio of probability of transformer and line damage, to the probability of failure due to transformer damage, which simply becomes 0.04 upon 0.2, which is 0.2. The next one asks us to find the probability that a given power failure which involves transformer damage, given there is a line damage. Just like the previous one, it will become the probability of transformer damage intersection line damage, upon the probability of failure due to line damage, which will be 0.04 upon 0.6, or 1 upon 15. The next one talks about the probability that a given power failure involves transformer damage, but no line damage. This time we need to calculate the probability of transformer damage intersection, not line damage. This can also be written as probability of failure due to transformer damage minus probability of failure due to both transformer and line damage. This becomes 0.2 minus 0.04, and that becomes equal to 0.16. Talking about the next one, it's now asking about the probability that the failure involves transformer damage, given there is no line damage. This can be solved just as our third problem, but this time we will take ratio of T intersection not L, upon probability of not L. And that will become 0.16 upon 1 minus 0.6, or 0.16 upon 0.4, which is equal to 0.4. The last one asks about the probability that a given power failure involves transformer damage or line damage. Here we need to recall the inclusion-exclusion principle from our previous video. We can write probability of failure due to transformer damage plus probability of failure due to line damage, minus probability of failure due to both the issues. So, this will become 0.2 plus 0.6 minus 0.04, and when we calculate this, we'll get 0.76. I expect that the concept of conditional probability is clear to you now. Thanks for watching. Do subscribe and share, and don't forget to give a thumbs up. I'll see you in the next video. Bye.